Hey guys, welcome to another channel episode. Remember, this is the channel where we talk all about how you don't need to be a CEO in order to have some impact on the world. And if you've been following along, you would know that I just started a new challenge. This challenge, of course, is to get through a data science bootcamp. Now, this is not an easy task, and it is really worth mentioning that this bootcamp has been kicking my ass, but a little bit more about the specifics coming in later. Alright guys, so welcome to another video. Thanks for joining me. This week, I'm going to talk all about my past week and how that's been going. These videos are mainly meant to be a kind of refresher for me, but also a way to document the hard work that has been going into learning data science for impact. Now, a lot of what I've been learning this week has been statistics. So if that doesn't really interest you and you think you can spend your time learning something else in another video, definitely go check that video out, whatever that video is. But if you're interested in knowing what I learned in a week of 8 hours plus a day studying statistics, this video is for you. Alright, so now let's get started. This week I learned all about all the statistical distributions and a little bit about Bayes. Now, let's first start with Bayes. Bayes is incredible. It almost makes the rest of, traditional frequentist statistics obsolete, but at the same time, not really. And let me explain. Now, there's two types of statistics out there, and they're kind of fighting. I don't know why, but one wants to be better than the other, and I think that there's enough space for them to coexist. Statistics is a growing field, and in fact, it's more necessary now than ever, so we want every tool possible. Of course, due to our change in tool set in statistics, going from writing things out through pencil and paper and just using a calculator, we can now use computers to do absolutely everything for us 100% accurately. And that means that our statistical methods can change. Now, due to the computation power increase in the last couple of years, Bayesian statistics has been having kind of its renaissance moment where a lot of people are switching over to using Bayes much more frequently than the traditional frequentist approach. Now, that does not mean as a data scientist or as someone who's trying to have some impact in the world, you shouldn't know traditional statistics. In fact, I would actually argue that traditional statistics, the frequentist approach, is still very, very necessary for almost all aspects of statistics. It just so happens that Bayes is a little bit newer, a little bit nicer for computational power, and it actually runs a lot of neural networks, and that's why it's all the hype. More on neural networks coming in just a couple of weeks, by the way. Alright, so that was a little bit on Bayes and the whole history behind kind of the two factions that are fighting. Again, in my opinion, it's a waste. You gotta learn all of it if you really want to know what impact you can have on the world. Now, moving on, the Bayes was very, very interesting because Bayes is a lot more thinking in kind of the human approach of things. You kind of update your possibilities on the fly, and you get a lot of prior experience into your knowledge about the probabilities of certain things happening. That's something that the frequentist approach cannot really do. They can't really update. They can only use current data and test using hypothesis testing. More on hypothesis testing coming up soon. So Bayes follows this premise where you can learn stuff on the fly and you can update your values in the Bayes formula, which is amazing and really simple to understand. Because of that, you basically end up with a much more traditional approach that learns way more like a human does. So this is why it's actually the backbone of a lot of neural networks and why it's all the hype these days. Now, moving on to what I learned before Bayes was the more traditional frequentist approach. This approach is the approach that most of you guys learned in school, and it is one of the backbones of statistics, which is hypothesis testing. So the idea behind hypothesis testing is you have a hypothesis that everything is the same, and if you find out that everything is not the same, if your data tells you that things are different than what you expect, you would then reject the null hypothesis. This is a little bit different than how they do things in science. So how does that work with data? So you have data that you collected of a certain event, right? And let's make that event the amount of food that you eat in a day. And you collect the amount of food you eat in a day in calories, and you weigh yourself at the end of the day. And you do this for a year. So you have 365 different points of data. And you have two columns, right? And at the end of the year, you have a hypothesis that the months that you ate less, you probably lost more weight, and the ones that you ate more, you probably gained weight. So your null hypothesis would be that those months would be the same as the other months. So let's split it up actually to make it easier between the early months and the later months. Now, the early months, the first 6 months of the year, you ate less, and the second period of months you ate more. And your hypothesis is that the ones you ate more probably made you gain weight. But in order to test this, to see if the data has this, you need to do hypothesis testing. This is the traditional frequentist approach. Now, we then have a null hypothesis that I mentioned earlier. In the null hypothesis, we would say that things stayed the same, and then we would test to see if that is true. In order to find the value that we used in order to reject or accept the null hypothesis, we need to do a z-score, which is pretty simple, and it's an easy formula you can find online. And then after you do that, you have to find the respective p-value, and once you find the p-value, you have to compare it to your significance level. Now, your significance level for statistics is almost always 5%, 0.05. Now, if your p-value is lower than that, you would definitely reject the null hypothesis because there is definitely evidence showing that you have gained weight. Now, if it is more than the significance level of 5%, then you probably don't have enough information here to reject the null hypothesis, and therefore you've probably didn't gain weight eating more food, which is good for you. Now, other things I've learned this week are just all about distributions. There are multiple distributions out there, and in fact, while I did know a little bit of these distributions before going into this boot camp, I actually realized that learning how to use these distributions through computation, through Python, has actually made me understand and grasp these concepts even more. Let me explain. So, when you start using Python to graph these distributions, you actually end up seeing your data visually instantly. You can have a bunch of different data sets and you can conduct this analysis of trying to find out what kind of distribution this matches. You can run multiple tests using this method where you can run simulations in Python, and so you can make your data set basically grow if you need to. You can do things like the bootstrap method, which allows you to pick a lot of points with replacement from your data set and create new samples that you then use. And I mean, so much more things. You can use the central limit theorem in order to test to see. Well, first you can do a test to see if it is normal. It's called the D'Agostino's, actually, the D'Agostino's Pearson test to see if a distribution of a dataset is normal. And if it is, you can then use the central limit theorem. Although most of the time, not all the time, but most of the time, if you look at your graph and it looks pretty good and you got more than 30 data points, you've probably got a normal distribution, and that is how we got the normal distribution actually. But it's always good to conduct the test. It's super easy using Python, like I mentioned, and then you can do these tests like the hypothesis testing, getting the z-score, and getting the p-value, like I mentioned earlier. So, of course, not every distribution is going to be normal. That's why you have to learn all the other distributions. But as it turns out, a lot of them are, and if you do the test, you can then do this thing where you kind of move away from using the data set and start using a more kind of abstracted view of your data, which allows you to then use a lot more tools. So that's actually one of the reasons why the central limit theorem is one of the most important things, and that's why you should always test for normality, because if you do have a normal data set, you are in luck because you got so many more tools to use. If you don't, that's okay. There's other tools that we learned this week to deal with that, but hey, normal data sets are awesome. And that's kind of just a small snippet of what I learned this week. I've got a lot more to study before these concepts really get into my brain and soak in, but I've learned that through graphing and through Python, you can learn stats way faster, as mentioned in my earlier book that I did during my Learning Data Science in 6 Months series, and there's also other videos that you can look on my experience going through that book, so I definitely suggest you check out those videos. But for now, I think that that's it. That's kind of been my week. It's been a lot of hard work, but I've produced a lot of good content from that and a bunch of really good coding. So I'm super excited to continue my journey and see what impact I can have on the world. So thanks for joining me for this video, and I'll see you next time.